talked about two systems of the body, right? Miss Sarno. Hi, Miss Sarno. Miss Sarno, what is the integumentary system? What is the integumentary system made up of?
Our head, fin, and nail.
Bam. Thank you very much, Miss Sarno. I really appreciate that. And Miss Trotter, what is the skeletal system made up of?
It's made up of the bones. Oh gosh. I know joints, but not all the joints.
No, all joints. All joints would be thrown in there. Sure.
My bad.
So.
And then was it ligaments?
Yes. Why ligaments, Miss Trotter? Because they're not bone; they're soft tissue. So why'd you throw in ligaments? You are correct, by the way. But why ligaments?
Because they connect the muscle to the bone.
How about they connect the bone to the bone?
Oh, bone to the bone. Yeah.
Yeah, that's why they're.
I was assuming the what are they called?
You switch stuff? Is that what you're talking about?
Yeah, because it was the ligaments and then the tendons. So those are the ones that connect the muscle to the bone, right?
Yes. And everybody seems to make this mistake, so don't feel bad. I mean, I have like seniors, and I'm like, what connects bone to bone? And they're messing up, and I'm like, dude, come on. Ligaments connect bone to bone. Okay, but today we're not going to be talking about ligaments. Today we'll be talking about muscles and tendons, because we're going to talk about the muscular system. Yeah, the system of the body that we're going to be spending most of our time with. It's kind of cool. We won't be actually talking about particular muscles today. We'll be talking about how muscles work and things that you should be aware of when it comes to muscles, all that kind of stuff. Okay, so let me share my presentation with you wonderful people here. Let's take it from there. And we should have the muscular system and pathologies. Okay. Just some important prefixes or suffixes or root words to know. My, as in my, means muscle. So when you see myology, it's the study of muscle, because ology means study of. But the reason I'm telling you about my is you're going to see my a lot, like myofascial therapist. That just means muscular fascial therapist. And some people will be like, are you a myofascial therapist? Trust me, everybody should be a myofascial therapist. Are you working with muscles and fascia? Yeah, you're a myofascial therapist. By the way, we're going to find out that muscles are coated in fascia. You can't really work a muscle without working fascia. Fascia is what gives muscle their structure. So, actually, fascia is what gives muscle its structure. Who here likes filet mignon? You ever had filet mignon? One person? Nobody? You guys don't eat filet mignon? Nothing. You're students. You're broke. You don't know what it is, right? It's an extremely tender steak. Well, the reason it's extremely tender is it has very little fascia in it. Your tougher pieces of meat that you find very tough, and that Mr. Blige will know, you cook them long, low, and slow. You're doing that on the tougher pieces of meat, not to break down the meat, but to break down the fascia in the meat so it's more tender. Because fascia is what gives muscle its structure. Muscle itself is actually very soft. Okay, moving right along. So, just like we said, the integumentary system was hair, skin, and nails and related glands. And then we said the skeletal system is bones, joints, ligaments, and any associated soft tissue around those joints, whatever, but bones, joints, and ligaments. The muscular system is made up of really muscles, really muscles and related fascial structures, but I would just say muscles and tendons. So if you want a really quick answer, if I ask you tomorrow, what's the muscular system, you could really say muscles and tendons. I'm going to elaborate on that right now a little bit, but like sometimes I like to give you information that you should have 5 years from now. 5 years from now, if somebody says, what's the muscular system, you could be like, pretty much muscles and tendons. There are 3 types of muscle. There are 3 types of muscle, and there's some things chemically that differ them, but they're still fairly similar. But those are cardiac smooth and skeletal muscle. So Your cardiac muscle is only found in one place in your body. Anyone want to guess where you find cardiac muscle? Miss Trotter just mouthed it. Miss McDowell just made, yes, the heart. It is the heart. Thank you. Your heart muscle is a particular type of muscle, and it's called cardiac muscle. So we will never massage that muscle except with our kind, loving words. And the heart is quite amazing if you think about it. It really is, we're going to get to it later, but it really is a pump that's about the size of my fist that pumps gallons and gallons and gallons of blood every day. And it starts pumping from the time before you're born to the time you die. And just imagine if you did this with your hand and just kept doing this for the rest of this lecture and then the rest of your life, your hand would get kind of tired. Anyway, by the way, how does your heart keep pumping so well? It does it because it's got a massive blood flow to it. And it's got so much, blood is life, and it's got so much nutrient coming into it, it can keep going. So when people have heart attacks, usually it's because blood has gotten cut off to their heart, and it doesn't have enough nutrients, and it kind of messes it up. So cardiac muscle is one type. Smooth muscle we will not be massaging either, but it's really cool stuff. And smooth muscle is wrapped around all the tubes of your body. And most of the organs too. But all the tubes of your body. And let me give you examples of tubes. Some obvious tubes are this one right here. And goes all the way down to my butt. Because that's my gastrointestinal tube. It is actually wrapped around with muscle all the way down. And those muscles do a lot of stuff to kind of squeeze food along and get it out my body eventually. Yes, Mr. Blygen.
Yeah, that was an interesting description of that. Because I thought that I had IBS at one point, and they were describing how, like, I guess once everything goes down, your stomach makes contractions to help food pass through. And then if there's like a blockage or gas bubbles or something like that in there, your stomach begins to contract even more, which causes that gut-wrenching pain from IBS. Trying to pop the air bubble or pass food through, but ultimately it wasn't IBS, it was appendicitis, and I had to take it out.
Oh, yeah.
Yeah.
Those will kill you.
Didn't know.
Yeah. Okay, well, you didn't have IBS. You had appendicitis. Anyway, smooth muscle goes around my digestive tract. It also goes around all my veins and arteries. And I know I've said this before, but the benefit of that is that I can actually contract and restrict blood flow to areas or open it up. So you have variable, adjustable plumbing in your body. It's pretty cool. I would love it if the plumbing in my house was variable and adjustable. And I could be like, we're not using the kitchen sink right now. Let's squeeze the piping down to that. We're taking a hot shower in back. Let's open the piping up to that in back of the house so that you get the hot water. Your body literally does that. Literally. Yes, Mr. Brown.
So the heart is always continuously pumping, and the only time it's not pumping is when you die?
Pretty much, sir. I mean, or when you have a cardiac arrest, don't get me wrong. But it really does pump from birth, from what do they call that? Cradle to grave. Yeah.
And my question was, what makes the art, like like in action movies and stuff like that, they're always like, if you get shot in the artery, that's guaranteed death, like type stuff. What makes them so dangerous?
Arteries?
To where they're like, yeah, like different than just a normal blood vessel.
No, it's a great question. So the blood vessel, we're going to get into this when we get into the circulatory system, but I love saying stuff more than once. So the tubing, the plumbing leaving your heart, Mr. Brown, are called arteries. And the tubing coming back to your heart are called veins. Well, when stuff comes right out of the pump, there's a lot of pressure in it. So there's a lot of pressure in your arteries. But by the time they pump all the way down to my fingers and hands, stuff like that, and the blood gets back in veins and comes back to my heart, the veins don't have a lot of pressure in them. So if you cut a vein, it tends to go pss, 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 pss. But if you cut an artery, it tends to go psh, psh, psh. It just spurts. And if you cut a big artery, you've only got 5 pints of blood. So if you cut a big artery, it goes fast. So stuff like your neck, your underneath your arms, your inner thigh, like in between your groin, are not good places to be cut. Because if you hit an artery there, you bleed out very fast because it's under high pressure, sir. It's under higher pressure.
That makes sense. So because of the high pressure.
Because of the high pressure, yeah.
Thank you.
And it's just harder to, it's harder to stop. And if that ever does happen to you, sir, you really do tourniquet it as fast as possible and get somebody to call 911 as fast as possible. Time really is of the essence. Wrap anything you can around that limb to stop the bleeding. As hard as you have to. Yeah. Okay, so cardiac, that's your heart muscle. We're not going to really deal with that. Smooth muscle, we're not going to really deal with that. It's just important to be aware it's there. Although we do affect it secondarily sometimes by getting blood to come to the skin, you know, things like that. Everybody remember what we call it when the skin gets red? Lots of blood comes to it?
Circulation.
Circulation is correct. Actually, that's true. But I meant hyperemia. Hyperemia. Yeah. But you are correct, Ms. Barnes. It is circulation. That's true. And then the last form of muscle is skeletal muscle. All they mean by skeletal muscle is muscle that hooks to your skeleton. So why would we want muscle to hook to your skeleton? Or what would skeletal muscle do?
Move it.
Yes, this is the muscles that move you. Your skeleton, we already said your skeleton does all sorts of cool stuff. It creates red blood cells and white blood cells, and it stores minerals, and it stores fat, and it's amazing. But one of the main things that we care about as massage therapists is your skeleton acts as levers for your body. Levers for my body. And muscles grab onto these levers, muscles contract and move these levers. Kinesiology is all about the study of levers and muscles pulling on those levers to make them do stuff like this. So skeletal muscles are your movement muscles. And we have already studied about 8 or 9 of them, but we will study about 100. Important skeletal muscles. These are muscles that move you, by the way, or help you not move and stay in positions you want to, like a structural muscle. So I'm using muscles right now to stand here straight up and down that I can also use for movement. But the point is they are postural muscles as well. They help me with my posture. So these are structural muscles. These are the things that move you and give you structural integrity. It's amazing. And skeletal muscles can only do one thing. What is the one thing they can do? Yeah, Ms. Lobitz, I like the way you said it, because I'm getting really good with lip reading. That is the simplest way, and I agree. That's the way I would look at it. Anybody want to say what they do?
Shorten.
Shorten, yes. Shorten, contract. I think Ms. Lobitz said pull. I love that too. Shorten, contract, pull, get shorter, and whatever two things they're attached to then must move closer to each other somehow, right? Or the muscle has to tear, but we're not dealing with that. All right, cool. So, 3 types of muscle, right? Cool. Mr. Placencia, what are the 3 types of muscle? Maybe I should, he's like, I gotta get back on my phone now. You can whisper it, sir.
Yeah. Can you hear me?
Yeah!
Oh, no way. Okay. The 3 types are skeletal, smooth, and cardiac.
Thank you, sir. Moving right along. Smooth, cardiac, and skeletal. And kinesiology is the land that we are heading to. Kinesiology is the study of movement. Most massage schools claim to kind of get into kinesiology, but they don't really do it. And why would we care about kinesiology so much as massage therapists? Because most of our clients are having a problem with movement. Now, by the way, their problem might be lack of movement, but that's still a problem with movement. You know, they come in and they go, I can't turn my neck. Like, that's a problem with movement. So we are studying kinesiology so we can get better at facilitating movement in our clients. I guess that's what I want to say. But in order to learn kinesiology, you have to learn all the bones and all the muscles and what all the muscles do to the bones and how they pull on those levers so you can start to understand how complicated actions occur. And then you can understand how to make those complicated actions occur properly. So very exciting stuff. And by the way, I will say too, this is all very applicable if you later want to go become like a personal trainer or physical therapy assistant or things like that, because all this kinesiology transfers 100% into those fields. 100%. I have students go on quite often and become physical therapy assistants. Physical therapists too, but physical therapy assistants are a really easy jump from here. So it's stuff to think about. And very much ties into personal training, because you really start to understand why an exercise works the way it does and why form has to be a certain way, instead of just memorizing it. Okay. Your book uses a term called muscle tone, and what they mean is muscle tone as it refers to posture. I don't actually really care if you even remember this term, but I want you to understand something. When I'm standing here in front of you, what my muscles are doing unconsciously to me is tiny little strands are firing off, and when those strands get tired, other little strands start firing again to hold me in this position, and that's called muscle tone. It's this continuous kind of partial kind of firing that goes on that makes me be able to maintain a posture. Because your muscles make you, if I wasn't using my muscles right now, I would just collapse down here. Yeah. By the way, Mr. Blygen, do you have a question, or you just have your hand still up? No. Okay. No. Okay, cool. And another little side thing, won't come up for us very often, but muscles can perform and create heat generation, which is thermogenesis. And that's why, like, you shiver when you get cold. Your body's actually trying to activate your muscles and make them do little contractions to generate heat. This is why you get hot when you work out, because muscles do actually generate heat. They really are burning calories, essentially, and it really does let off heat. There is a thermodynamic reaction going on there. So muscles really do let out heat. Okay. This next part is tricky. So I'm going to take you guys over the whiteboard. I want to talk to you. I always keep saying, Tap's going to keep saying, muscles can only do one thing. They can only do one thing. They can contract, shorten, pull. That is 100% true. I want to talk a little bit about how that happens now. All right? So, okay. Sorry, Skelly. All right. So, hello. All right. So, first off, I want you to realize that muscles are highly specialized tissue. They're highly specialized cells that only do one thing. They only contract. That's all they do. And your muscles don't shorten as much as you might think. They shorten very powerfully, but not as much as you might think. So let me give you an example. Let's look at our elbow. So, this is Tap Scott's almost an exact replica of my hand. Do you notice how there's a tiny bit of line sticking below this other line here? That is truly your elbow, is how it works. So if this was your elbow and this is underneath on the posterior side, what muscle would be back here? Oh, I saw somebody mouth it. It made me happy.
Tricep.
Tricep.
Brachii.
All right, triceps. Oh, and she threw in brachii. Thank you. Cool. So you got the triceps brachii back here, right? It's this beautiful, like, three-headed muscle that I'm only going to draw one head of because I don't know what I'm doing, all right? And it does not look like an eggplant, but this is just what you get today. Okay. Here's what I want you to realize that's kind of amazing. If this hand is over here, right? Or over here, look how much distance this is. Look how much distance this is. My tricep only has to contract about an inch to get my arm to move that far because of how levers work. Do we understand that? So a tiny little movement down here gets a huge movement. Tiny little movement down here gets a huge movement up here. Tiny little movement here, that thing's on the other side of the screen. Tiny little movement here, but my movement down here was only that much. All right? This is key to your body. So what your body does is it takes a long muscle like this and it's just got to get that entire muscle to shorten itself by an inch. The entire muscle. And what it does to do that is it has tiny little muscular compartments in the muscle cell that shorten. And those compartments are called sarcomeres. So, inside our imaginary muscle here, our horribly drawn imaginary muscle, you can imagine a giant train. And that train is made up of cars. And I will explain what sarcomeres are in a minute. But sarcomeres are the contractile unit inside a muscular cell. But also sarcomeres have to do is contract like a little millimeter. Because if you put a whole lot of sarcomeres together, you're going to get your inch. If you had a railroad train, you guys watched a railroad train go by? There's like 238 cars. If you took an inch off each one of those cars, at the end of that train, you'd have a huge gap. Like you would have shortened that train by a fairly significant amount. And that's what your muscle fibers do. Your muscle fibers really do that. So these muscle fibers are made up of long trains of these sarcomeres. And these sarcomeres are the unit that actually contracts. And they're all connected to each other. So if every little one contracts just a little bit, the muscle goes doop. But it truly gets shorter. Okay? That's what my arm truly comes out here because my tricep gets shorter and I don't have a choice. Can't stop it. It's going to happen. It's actually shortening. Okay. So let's talk about these muscle fibers. And by the way, I'm trying to explain this contextually to you and thematically to you because when you leave here, Z-lines and all the stuff in the book isn't going to matter. Nobody's ever going to mention them again. But understanding that there's contractions happening in the muscle and there's contractile units is important. Does that make sense? I'm not very caught up in the words. Some of them you will use on today's test and we will never mention them again. And we know that. We want you to have heard them once, so if you ever read them in a paper or somebody brings them up again, there's some memory there. But what we want you to understand is just the concept of how a muscle cell works. Yeah? Okay. So, let's take a muscle. Muscles in your body are made up of really they're long cells. They're called myofibrils, but they're long muscular cells. Muscle cells are so strange that most of them run the entire length of your muscle. And think how small a cell is, and they run the entire length of your muscle. They're one of the only cells I can think of in your body that have multiple nucleus in them. They've got multiple brains operating them because they're so long. So in our pretend muscle here, this would be an actual muscle cell that's super long and skinny, another one 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 that's super long and skinny, so on. And when I say there's a lot, don't quote me on this, but because I don't know the exact numbers, but I can tell you like in my eyelid, there might be 100. And it takes about 10 muscle fibers to lift my eyelid. So you can imagine in my bicep, there might be, I don't know, 1 million, 2 million. In your quads and your legs, there might be, 100 million. There's a lot. So these fibers are much smaller than hair. And they're strong. I know you're like, well, it takes 10 fibers to lift an eyelid. Yeah, but these are tiny little guys. They're pretty impressive, okay? So inside each of these fibers are all these sarcomeres. These contractile units. And quite literally, they have some proteins in there. They have some proteins in there, and when they're activated by the right chemistry, these proteins in there actually kind of have little hands, and they grab each other and do this. They literally grab each other and pull a little bit. And it's a chemical thing, but it's really a physical thing happening. They pull because of a chemical reaction. Well, it's happening on a microscopic level, but if you have it happen in a whole bunch of sarcomeres, that microscopic level adds up to an inch or two. And an inch or two is all you need to get me from here, touching my shoulder, out to here. I just need to get an inch. So that's what happens. That's what happens. So muscle fibers really are muscle cells. Muscle cells are really long. Muscle cells have a whole bunch of sarcomeres in them. These sarcomeres are called the contractile unit, the thing that makes them shorten. And yes, Mr. Blygen, because I kind of forgot where I was going with that anyway. Yes, sir.
So the sarcomeres, for example, if we're looking to do this action with our arm, it's contracting something in our triceps brachii.
Yes.
So sarcomeres are, is it the ones that are closer to the joint that are activating, or is it all of them?
Oh, Mr. Blygen, you ask the best questions. So here's what's happening. Mr. Blygen asked a really interesting question that's actually a really important part to muscle theory that I do want you guys to remember. Muscles work on an all or nothing basis. So they work on an all or nothing basis. And so basically an entire muscle cell and all of its sarcomeres fire off, or it doesn't fire off at all. And so it's honestly like if we had a, oh geez, this is going to challenge me, sorry. We had some kind of stagecoach here, and I need to move it, and I've got a horse here. Do not ask me to draw a horse. Right? We tie it to the stagecoach. I would never do this to an animal, but I can whip that horse and it will run as hard as it can whether it moves that stagecoach or not. If it doesn't move the stagecoach, I need to get more horses. And that's how your muscles work. So what your muscles really do, like when I go to lift my eyelid up, my brain says, well, this is going to require 10 muscle fibers, and it tells 10 muscle fibers, give it your all. They don't know how to do a half contraction. So 10 fibers try as hard as they can, while the other 90 sit there and lazily watch them, and they go for it. So this is called muscle fiber recruitment. Muscles fire all or nothing. There are no lazy muscle fibers, ever. When a muscle fiber, a single muscle fiber, or a million muscle fibers try to fire, they work as hard as they know how. All their sarcomeres contract, all along the muscle, to answer your question, Mr. Blygen, but they all contract in that single fiber, that little hair-like, much smaller than hair-like cell. They all fire full power, and if your brain decides it needs more power, it recruits more horses. It gets more fibers going. It says, hey, you guys need to get up and help too, and it fires those. Yes. And when I'm standing here, like this, I'm using back muscles to stand here. They do get tired, and my brain, without me knowing it, says, all right, you 25 fibers that have been kind of holding them up, you take a break. We're going to bring another 25 online. But it does it seamlessly, by the way. It turns this one off, pops this one up, turns this one off, pops this one up. So it's constantly like, oh, these fibers are getting tired. It kicks in these other fibers. And I don't know because I got millions of fibers back there in the same back muscle, if that makes sense. All or nothing. Muscle fibers, not only can they only contract, they can't do anything but contract like hardcore. Mr. Riedel?
Yeah, I was going to ask, to go off of Mr. Blygen's question, but I think you kind of answered it. I was going to ask about how movements can kind of you move your arm halfway. You wouldn't be using all of your fibers then. You're just kind of using what you need to get your arm into a certain position. Yes.
So this may not sound like an answer what you're saying, but it really is. So when I'm moving something like this, I'm obviously not using my full strength. So my brain is very intelligent. I mean, your brain is doing a lot more stuff that you don't know about than stuff you do know about. And so my brain right now is like, give him enough power to lift this thing, recruit 35 fibers, because otherwise I'd be throwing stuff around the room. And so you're right, when I go halfway to something, what I do is let's say I recruit 100 fibers to lift my arm up, and then when I get to here, my brain says stop. It stops recruiting those guys, and maybe it has 10 fibers just holding it here. Or it recruits some tricep fibers and locks it in place. Keeps contracting these and contracts these to lock it in place. But you're absolutely right. But it's still, the fibers that are working, sir, are still working full force. You're just not using as many, and your brain might shut them off part way there. So yes, I can contract as hard as I possibly can with these fibers and then just choose to stop. Sure. Sure. But the fibers being used know nothing else except, yep, yes, boss, you told me to pull, I'm gonna pull. And they pull. Really hard. They're hard-working little suckers. Yeah, Miss Walker T.
So when you're lifting weights, right, and then you experience muscle failure, like you just cannot lift anymore, what is happening then?
Okay, you're a little quiet, but I think you said when you're lifting weights and you experience muscle soreness?
Muscle failure. Can you hear me now?
Oh, muscle failure.
Yeah.
Yeah. So what's happening there is that your muscles require a certain amount of time to recharge. They need calcium ions, believe it or not, to come back into your muscle and kind of recharge it, and they need energy in there. They need ATP in there, really, basically, to fire. And when they've used that up, it takes them a little bit of time and blood to fill that back up, and that's where your muscle fatigue is coming in from. And obviously, heavier weights give you muscle fatigue faster because you're using all your muscle fibers. If I'm using my whole 10 million muscle fibers in my leg, and all 10 million get tired at the same time because I was using all of them, then that's it. But if I was only using half of them, when those half get tired, the other half can kick in for a while. This is how you guys, by the way, run and bike and walk. You're not using your full muscle capacity when you run, bike, and walk. And so what happens is some of your running muscles get tired and your body kicks in other ones while the other ones, recoup. I should say some of the fibers in there do that. But anyway, yeah, so what's happening is you're running out of energy inside the cell, and the cell has to fuel back up again, literally. That's where muscle fatigue is. Yeah. Once it contracts, it's got to refuel the contracting pumps, essentially. So this is an important picture here, not because of the words around it, not anything like that, but for you guys to get an idea of how fascia works. So this is a cross-section of somebody's arm, right? And this is supposed to be a cross-section of a single muscle. And what they're trying to show you is if you go down all the way to the microfilaments, the myofibrils, which is the muscle cells that look like tiny little hairs, groups of those are wrapped in fascia, and then groups of those are wrapped in fascia, and then groups of those are wrapped in fascia, and then the whole thing is wrapped in fascia. Very, very much like insulating wire around electrical wire. If you've ever seen really large electrical wire with lots of stuff running through it, all the tiny wires are wrapped with plastic, and then they put groups of those around and wrap them with plastic, and they're in bundles, and those are wrapped with plastic, and the whole thing is in this big plastic sheath. Very much your muscles are like that too. Does that make sense? I'm not seeing a lot of aha looks. Kind of, sort of, maybe. Okay. There are some names for the fascia around these. So, who can tell me the 3 layers of skin from your integumentary system?
Epidermis, dermis, and I want to say it was subcutaneous.
Yeah, epidermis, dermis. Subcutaneous is 100% correct. There are 2 other names for that.
I don't remember. I don't have them. I have the notes, but my flashcards.
Oh, it's all right, sir. I appreciate your answering. So and by the way, I'm not looking for another answer because he's wrong, but I'm looking for another answer to make a point. So who can tell me what the other two names are for the subcutaneous layer?
I think one of them is hypodermis or
Hypodermis, which means
Hypodermis.
underneath the dermis. I love that one. And what's the last one, which is ironically the one I want? But again,
I
not
think it has
because you're...
something to do with sub.
How about super?
Oh.
Superficial.
Superficial fascia. Do we remember why we called it superficial fascia?
That was the most superficial layer of fascia.
Right. So we call it hypodermis because it is the lowest layer of dermis, but we call it superficial fascia because it's the highest layer of fascia. It's because we're about to go down to deeper layers, because underneath that skin layer of fascia is muscular fascia, right? And the first layer of muscular fascia is epimyosin. I just want to make sure I'm spelling it right. Epimysium. Epimysium. And this tends to be the stuff that's around multiple muscle bundles and such. Epimysium. And then around smaller bundles, there's paramysium. And around the actual individual fibers, protecting them, giving them integrity, making sure they don't stretch too far, keeping them safe, is endomysium. Yeah. Anybody remember the fascia around bones?
Peristeum or something like that.
What? Ms. Walker?
Like the peristeum.
Paraosteum. Because osteo means bone. Periosteum. Because these eventually connect into bone. Periosteum. Alright. So if we were to, because you know, I always have to kill somebody in a lecture. So if we were to kill somebody and we were to cut through their skin, first we would cut through the epidermis. We wouldn't see much blood here, right? Remember, the epidermis is basically dead, except the lower layers. Then we get to the meaty, juicy dermis. It's the thickest part of the skin. And what happens? We start to see a lot of blood. Then we get down to this kind of thin, kind of strong layer. And it's kind of wrapped around everything, around like the entire leg, let's say, if that's what we're cutting into. And that's superficial fascia. But then we notice the muscles themselves are kind of wrapped in this thick fascia called epimysium. But we cut down through that and we notice there's muscular bundles within that are wrapped in paramysium. And then we notice we break it down into little tiny fibers, and even those are wrapped with something called endomysium. It's all the same. It's all fascia. It's all the same stuff. Anybody here ever boiled chicken breast and then shredded it? Okay. It shreds along the fascial lines. Like, why doesn't it ball up? That's not what it does. It shreds in strands. Those strands are fascia wrapped around. Those strands are paramysium strands. It's because if they were endomysium strands, you wouldn't even see them. They'd be so small. So it's groups of muscle wrapped in fascia, and it tears along those lines because the fascia is holding the muscle together, and so it tears down those lines. That's why you get those nice long stringy lines of muscle. Those are bundles of muscle cells wrapped in fascia. And this is all important because what we want you to realize is you are really massaging layers and layers of fascia. And all this fascia from the muscle literally weaves into the fascia of the bone, the periosteum. The muscle's job is not to be strong. Muscles are not strong. They tear very, very easily. The fascia in them keeps them from tearing. Muscles are very strong in the sense that they pull. That's what they do. They're hiding out in those long chains ready to pull. But it's the fascia that actually keeps them stable, especially when you're stretching them, keeps you from tearing them, all that stuff. And it's the fascia that actually attaches to the bone. Have you ever tried to pull a really long sock off your foot from the toe? Yeah, I see some people laughing, right? It doesn't work very well, right? Right? Because it kind of grabs onto your whole leg. Well, that is actually a very good example of where tendons come from. So tendons attach muscle to bone, right? The problem is with that concept, we've been teaching that to people forever, and it's 100% true, but it's misleading, as many things are in anatomy. Because it makes you think you've got a muscle here. Oh, jeez. Let's do a good one. It makes you think that you've got a muscle here and a bone here. And it makes you think this section right here is a tendon. But the whole thing is a tendon. The section at the end is just missing the muscle. Just like your sock, when you pulled it out over your toe, all you were holding was sock at the end, but the sock runs all the way up your leg. The fascia's always been there. What happens is at the end of the muscle, there's no more contractile tissue, there's no more muscle, and all that's left is all these wrappings, and they feed into the periosteum of the bone. Except instead of a sock around your foot, it's a sock around groups of socks, around groups of socks, around groups of socks, and all those socks are coming off your foot. And the area at the end we call a tendon just because there's no foot in there. Okay, cool. Good stuff. And muscles are highly vascular, tendons are highly avascular. So one of the tricks that we use in massage therapy, I know it's not a trick actually, one of the things we focus on in massage therapy that is pretty universally agreed with is we focus on origins and insertions for multiple reasons, but one of the reasons is because they are avascular zones that need extra stimulation. Please keep rubbing muscles. I don't know why you would stop, but pure muscular problems are not that hard to deal with. Where they insert is often where the problem is. Plus, we like to emphasize origin insertion so that your strokes are long. We don't want you just, being like, okay, I rubbed the bicep. No, we want you to start from the beginning, get all the way up and do the whole thing. I talked about that in some of the labs today, right? Lengthening your strokes. And so that's why we focus on origin insertion too. But the other reason is because we really care about avascular attachment sites. Yeah. Cool. All right. Yeah? You okay there, Mr. Blygen? You rubbed your head. I just don't know if that's a good sign or not. Is that the knowledge banging its way into your brain? No? Okay. Okay. Let's see. Let's see. No. I don't want to get too technical into some of this with you guys. You will hear, definitely in your test tonight too, the two main proteins that are responsible for contractions in your sarcomeres, which are in your muscle fibers, which make up your muscles, are actin and myosin. These are the two main proteins that inside your sarcomeres actually kind of grab each other and pull themselves together. Yeah. Yeah. And these actin and myosin proteins, which we don't need to fully understand, believe me, but they show up as thick and thin filaments within the sarcomeres, and those thick and thin filaments in these sarcomeres create a striped appearance. And it's the reason they call skeletal muscle striated. That was a long story to explain why they call skeletal muscle striated. Cardiac muscle is also striated too, but it's a different type. But skeletal muscle is striated muscle. That's a very common way to talk about it. And it means striped. It's striped. But it's striped because these thin and thick filaments that are little hair-like things inside the sarcomeres, that are the key to them being able to contract. That's why you have striated muscle. And your book's going to mention this. I don't think it's important at all. But between these thick and thin filaments, there are what they call Z lines that attach them, kind of attach all the sarcomeres together. It's not important for us at all. I just wanted you to understand. It's somebody naming a junction between these areas. Okay. Woo! Questions so far? No. Okay. Can understand that. Let's not do that. This is just a picture of the thick and thin filaments that are made with myosin and actin. And it's very hard to explain, but those kind of like nice bow and arrow kind of looking things, they will actually grab and move and change and actually create the contraction of your muscle. There really is truly a physical pulling that goes on inside your muscles. There really are these little guys that kind of, they change when they're set off by a chemical reaction. We don't need any of that. Okay, I've already talked to you guys about endomysium, paramysium, and epimysium. It's all the same stuff. It's fascia. It's just like superficial fascia. Just remember now, we're learning about bags around bags around bags around bags. Everything is insulated. Everything is wrapped in your body. And getting a muscle to change is pretty easy. Getting the fascia to change takes longer. So a lot of times when we think we're stretching somebody's muscle, we're probably really stretching the fascia in their muscle. Because every fiber is wrapped with endomysium, end, the last one. Right? Every single, these little microscopic fibers are all wrapped in this plastic wrap, fascia. And then groups of them are wrapped in paramysium, big groups are wrapped in endomysium, and entire legs and stuff like that are wrapped in superficial fascia. So you have got a lot of fascia in your body. Remember, it's the most prominent tissue in your body. Most prominent tissue in your body is connective tissue. You are bags and bags and bags and bags of fascia. Cool. Let's take a break right here because then we'll come back and talk about fascia a little bit more and tie some stuff together. But let's take our 15-minute break right now if it's okay. Yeah? All right. It is okay. Good. See you guys in 15 minutes, which would be 4:43. 4:43. Thank you, everybody. Thank you. Oh. 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 Too funny. It's called ligaments, and we tend to see the matrix in it kind of run like this. I'm not saying there aren't cross fibers, but we tend to see them in the direction of stress. It makes a lot of sense. And we see the same thing for tendons, which attach muscle to bone. Tendons attach muscle to bone, and we tend to see the fascia in there kind of run in this direction. Well, with aponeuroses are big sheet-like tendons, big sheet-like fascia. And there we see the matrix go very crisscross. So it might be a big sheet of fascia here, and we see the matrix actually go very crisscross. Why? Why? Because aponeuroses aren't connecting just one bone to another. They're designed to handle stress from all directions. And so the connective fibers run in all directions, if that makes sense. Anybody know places on our body where we have aponeuroses? There's 3 big ones.
In the wrist.
That's very good, sir, but that's retinacula.
Oh.
But, by the way, sir, they're the same thing. Retinacula is just ribbon-like aponeuroses, really. So, like when you see a gymnast tape up their hand, well, Mother Nature's already taped up the inside already, and it looks exactly the same. So that's ribbon-like fascia, and you find it in your wrists and your ankles, and it's literally there for the same reason that gymnasts wrap up their wrists and ankles. It's there to support your wrists and ankles. You all have it. That's retinacula.
Is it one like in the elbow?
No.
No.
I mean, don't get me wrong, there's little aponeuroses everywhere, but there's 3 really big spots on your body.
Sternum.
Abdominal aponeuroses. There is, by the way, there is fascia over your sternum. You're absolutely right. But abdominal aponeuroses. Then, remember thoracolumbar aponeuroses? So, some of you saw me putting an elbow into somebody's back today with about 200 pounds of pressure. And we were like, whoa, how can you do that? It's not just the muscles in their back. It's they've got thoracolumbar aponeuroses in there. They have a sheet-like tendon back there that's indestructible. Yeah. So you've got a very big aponeurotic sheet on your tummy and on your low back so that your body can link them all together with abdominal muscles and give you a lot of strength there. And then we've also got one on the top of our head called the Gallia aponeuroses. That's up here too. That's like a shower cap up here that allows me to suspend muscles and things like that. But those are great examples of aponeuroses, which are just sheet-like tendons, sheet-like fascia. But we tend to see the fiber matrix in them go lots of different directions because you don't know which direction the sheet's going to get pulled on. And this is very much how we make sheets and how we make ropes. If I make a rope and I'm going to tow your car with it or whatever, or I don't know, we're going to go mountain climbing, we have the fibers go down the rope. We might twist them, but they go down the rope because that's how they're going to get pulled. We don't have them going off the sides. But a bed sheet, we have the fibers going in multiple directions. We don't know which way we're going to pull on that sheet. It's got to be strong in all directions. So that's the way you kind of tell aponeuroses and retinacula and tendons and ligaments apart. They're all connective tissue. It's all kind of the white connective tissue that you've accidentally chewed on or peeled off a piece of chicken or something like that, but it's in different forms. That's it. So usually when I'm talking about aponeuroses, I'm talking about very thin sheets of it. So usually when we're talking about stuff like superficial fascia and endomysium and paramysium and epimysium, we're talking about very thin sheets of fascia wrapping around stuff. But we do see fascia in other forms, like tendons that attach muscle to bone, ligaments that attach bone to bone, aponeuroses that provide big supportive connective tissue sheets in your body, and retinacula, which is ribbon-like wrappings for your wrists and ankles. Those are really good examples. And I'm not sure all those should be in the muscular system section, but I also admit I'm not sure what other section I would put them in either. I'm just saying tendons makes perfect sense, but aponeuroses, I don't know. Although muscles do insert into aponeuroses, so maybe that's why they put it in here. So like in your low back, where the thoracolumbar aponeurosis is, which is in your low back, in your lumbar area, things like your latissimus dorsi and stuff like that. I know the book says it inserts into certain spinous processes and stuff like that, but it also, all that stuff back there inserts into the fascia back there. And that fascia inserts into your hips and into your glutes and keeps on going. Very significant. Okie dokie. We've already talked about some of this stuff. We've talked about origins and insertions, but just so we're really clear, this little fat part of the muscle is called the muscle belly, and it's where most of the contractile tissue is. It's where the actual muscle is. If you were going to have a steak, that's where you'd cut your steak from. The end is where the tendon is. And these ends attach to bones, right? These ends attach to bones. Both of those ends are called attachment sites. Both of those ends are called attachment sites, but we usually name one as an origin and one as an insertion. They're both attachment sites because they're both attached here. I actually prefer just calling them attachment sites. But usually the origin is the bone that's stubborn enough to stay there. Usually the origin is more towards the center of the body, and it's the bone that's not moving. This is usually the arm, leg, finger, toe out here, which is the insertion. So the insertion is the attachment that moves. The origin is the attachment that doesn't move. Usually the insertion gets closer to the origin. Is that always true? No. Do we flip the names when it's not true? No, we still keep calling them origin insertion. But there are many examples when the origin moves closer to the insertion. It's just a general thing. So I don't like worrying about it too much. I just want you to be able to find muscles. And the way you find muscles is knowing their attachments. It doesn't matter what you call it. If you can find the attachments, you can find the muscles. And that's really, really true. Think about it. You know, when you're driving someplace, you're looking for landmarks. Oh, there's that gas station there, and that's where that street sign is that I'm looking for, right? And we do the same thing on the human body. I did it today successfully, by the way, with everybody I did it with, where I grabbed their shoulders and said, hey, what muscle is this on there? And they're like, well, that's the supraspinatus. And the way I found it and the way they knew was I found the spine of their scapula, and then I popped on top of it, and they knew right away where I was. So, because I knew the attachment. I knew the attachment is right above that spine of the scapula. That's why this is so important. Because it's hard finding stuff in people's bodies. Right? Everybody's different. Okay. By the way, your book calls when origins and insertions switch functional reversibility. I've never heard anybody use that word in my life, except me, in this lecture. So we just learned about this muscle, right? This is your biceps brachii. And it really is the muscle belly that shortens, that really does pull the arm up and lift that ball up, right? Now, are all the fibers in the biceps brachii firing to lift this ball up? I hope not. I doubt it, unless it's a very heavy ball. Your body is just firing enough fibers inside that muscle to get the ball to raise up. Maybe 100, maybe 1,000 fibers. maybe 10,000, but not a lot, right? Remember, muscles, the fibers work on all or nothing. All your muscles are made up of 1,000,000 fibers, and your body is only just firing off a few to get you to do something. Or all, by the way, if it's the heaviest thing you've ever lifted, it's your absolute max. It could be all, but it's unusual. I'm sorry, I'm pausing because your book talks about properties of contraction, and I'm not sure how these help you as a massage therapist. So, but muscles, your book will say muscles have the property of excitation. They can be excited, and that is true. They are in a resting position, in general, full of energy, ready to fire until you excite them. And you actually really do send a nerve pulse from your brain, down my spine, out a nerve plexus, down to the muscle I want to fire, oh, it's going to be my thumb muscle today, beep. And that releases a chemical messenger that actually tells my muscle to fire, and it releases calcium ions, things like that. And then all the little sarcomeres go, okay, for however many ones we set off. If it was a really hard contraction, my brain might have sent a lot of messages down there to a lot of muscle fibers. But that's it. That's excitation. The ability for it to be excitable, for it to be set off. That once it's full of fuel, it's ready to go, and it will ignite. That's excitation. Contraction is the thing that I always keep talking to you about, right? The muscle can shorten, it's got actin and myosin inside it, and those proteins can work together, and they actually have thick and thin filaments that actually grab onto each other and pull each other closer, and you've got loads and loads of sarcomeres in every single muscle cell, and they shorten that cell, and that's how you contract, and that's the only thing muscles can really do is contract. Now, your book says they have extensibility, which means they can extend. Yes, they can. That means they can be stretched. But the muscle's not stretching itself. Does that make sense? My bicep can contract. My bicep can't, stretch itself back out. That's the job of my tricep or my other arm. Yes, the tissue can stretch. It is extendable and it can stretch, and muscle tissue can stretch, really because the fascia inside it can stretch, right? But I just want to be very clear. It's not a power of the muscle. It doesn't do it. It's an ability of the muscle. It can be stretched. It is elastic. It's elastic because of the fascia in it, by the way. And then this elasticity is also due to the fascia, actually, because fascia has elastin in it. It's got a property that's really like rubber bands, so it will go back to its pre-contractile state. It'll just kind of fall back into place. But it's not pushing itself back into place, all that kind of stuff. It can only do one thing on its own power, which is pull and shorten. And then let go. It can choose to let go. It does all the time. But that's just stopping doing its job. It can never push. Never ever push. Okay. So, how do you know to fire muscle fibers? Well, your brain actually has wires, neurons, from your nervous system, which will be another system of the body that we will study. And it really does send that signal down that I was sillily doing there, where I said dee 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 dee, and it goes down my arm. Well, that dee 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 might go to one fiber. Usually it doesn't. Usually it goes to more than that. It might go to 10, it might go to 100, it might go to 1,000. But your brain has wires going to small groups, large groups, really big groups, lots of groups, lots and lots of wires. So it's not like I have one wire going to my biceps. My biceps brachii has hundreds of nerves going to them, so that my brain can be like, yeah, fire that group of 10, fire that group of 100, fire that group, depending on what it needs to do. And these nerves, we're going to find out later when we do the nervous system, work on an all or nothing thing too. They're like a light switch. There is no dimmer switch on the nerves. I can't be like, gently fire that muscle. No. Nerve is like, yes, sir, firing that muscle full force. Tells the muscle fire full force, the muscle fires full force. The nerve yells as loud as it can yell. It does one thing, it carries a message, it's either on or off. The muscle does its thing either on or off. Again, your brain controls this by how many nerves it fires up here. It goes, wow, that rock looks really heavy. fires a whole bunch of nerves, gets a whole bunch of muscles recruiting. But that's how it works. It's just like a light switch in the room, and that light switch turns on a light, and if I want more lightness in the room, I turn on more light switches. But they're either on or off. Cool? All or nothing. Nerves are all or nothing. Muscles are all or nothing when it comes to this. And the nerves, the wires, by the way, you've got wires coming out telling muscles what to do, and you've got wires coming in telling you what you feel and all sorts of stuff. There's wires everywhere. That's your nervous system. It's just a communication system. But the ones that tell your muscles what to do, we call those wires, even though they're just like all the other wires, but these ones are hooked up to tell muscles what to do. We call those motor neurons. Those are the nervous wires that are hooked to tell my motor units what to do, and my motor units are my muscular fibers. So those are motor neurons. And at the end of these motor neurons is something called acetylcholine that is a neurotransmitter. That is a big fancy name, but what it really means is that it helps the nerve to transmit its message. Because at the end when it gets to the muscle, it actually kicks off this neurotransmitter, this acetylcholine. And the acetylcholine is actually what tells the muscle to fire. That's what happens. So it doesn't actually send an electrical shock right into the muscle, although that can work. It actually releases acetylcholine. The acetylcholine tells the muscle to fire. Now there is a little gap between the nerve fiber and the muscle, and this is called the synaptic gap, and that's what the acetylcholine has to go kind of float across in your body to get to the nerve. This all happens very quick. But that's called your synaptic gap. You've actually got synaptic gaps all over the place in your nervous system. You've got them in your brain, you've got them between your nerves and all sorts of stuff. And they're good. If your synaptic gaps fire too well, you tend to get kind of tremors and things like that, because they're firing off too easily. So they kind of buffer your system a little bit. And we'll talk about that more when we get to the nervous system. Right now, where we are right now is you've got a boatload of muscle fibers in every single muscle. They all either do their entire job or nothing. It's all about how many we recruit, and that means it's about how many motor neurons tell those guys to do their job. That's it. Yeah? Yeah. Okay. Good. Good picture of a synaptic gap here, though. And acetylcholine telling the muscle it's time to fire. And remember, the muscle just goes, okay, all right. Not the whole muscle, but whatever fibers. It's like, okay, we're doing it. We're not going to worry about that. Yes, Miss Estes.
Okay, so information like this, would this be on the MBLEX test?
I don't know, because I've never taken the darn test. But I have a substitute teacher who works here who has taken it. And we can get her in here to talk to you. I have no problem with that. Because she'd be the best authority to take it. Here's the thing that bothered, and by the way, what she told me was on the test was she said there's an awful lot of pathology on the test. So there's an awful lot of questions about, like, so-and-so has this condition, and so you really need to study your pathology. She thought that was the hard part. And I'm pretty sure the other thing she told me that I found really annoying was I kind of wanted to find out how well she passed the test, because I know how good a student she is, and it let me gauge how hard it is to pass this test. Mm-hmm. And I think what she told me is they don't tell you how much you pass by. Mm-hmm. Which is really kind of crappy, because it makes it very hard to gauge the test. Right? We're like, is it like, she's a very good student, but maybe she aced it. She said it was hard, but she passed it. And I have a friend, by the way, who I think is super smart, by the way, and I'm not just saying this to be nice. I think she's super smart, but she's not a super smart, book smart person, right? Mm-hmm. And she took it and she passed it. But she took it some time ago and they have changed it since then. So I'm not an authority and I don't know, but it's Day-Nutil. It's Miss Day-Nutil, and I'll have her come in and talk to you. I have no problem with that, about the MBLEX as best as she knows. But I'm worried the problem is she's not going to know everything, because I'm worried they didn't tell her. Like, I wanted to come back and be like, oh yeah, I scored X and X on pathology, and then we could kind of reassemble, like, well, what should we be focusing on? Yeah. I don't think, from what she shared with me, stuff like myosin and actin are going to be on there a lot.
Okay, just curious.
Yeah. But the problem is, a lot of these tricky tests require some backstory in your head. Where you're like, well, I don't know that thing, but I know we now have to have acetylcholine present for the muscle fiber, and you're telling me it's fire, and you're telling me it's not there. So maybe, you know what I mean? You have to kind of put stuff together. Yeah. Yeah.
Okay.
Yeah. I also do know, and this is kind of I'm referring you now to another source, but I also know that there are online things that you can pay like $99 for, and they promise to help you study for the MBLEX, and if you don't pass, you get a free subscription until you do pass. And they ask you, there are thousands of MBLEX questions, and obviously there's only 100 on the test or whatever, but they drill you on those questions. And so that's a good approach to take, yes. Yeah. But at the bare minimum, yes, I would say that you need more backstory than, this is the type of backstory you need to take that test, yes. And the sad thing is that she told me too, is she said there really wasn't that much muscular anatomy on there, which I was shocked about, because it should be the number one thing on there. And that's not just a TAPSCOT thing. I think most massage therapists would say, yeah, muscular anatomy should be the first thing on there. And she said there wasn't a lot on there. Now, I don't know if that's because it came easy to her and she felt that way or what, but she just felt like there wasn't. And to add even more to this, I have heard, although I feel like I'm talking about rumor now, but I mean, I've heard some fairly reliable sources. It's a computerized test, and it gives you more difficult questions if you answer these correctly. And so it's possible that she answered her anatomy so well that it finally said we don't have to ask her those anymore. So she thought she didn't get a lot of anatomy questions because the computer figured out really quick, person aced anatomy, let's go on to pathology, that kind of thing. And so they've really well designed it so we can't outsmart the test, right? So you can't go take it and you and I can't talk and just kind of ace this test. Yeah.
Interesting.
Very interesting.
Thank
Very
you.
annoying. Yeah, thank you for nothing. Sorry. But let me know. Let me know. I'll have her come in and talk. She works for us, so I have no problem. She's awesome.
Okay.
She's awesome.
Thanks.
And I wouldn't be opposed to us creating a MBLEX study course of some kind. For people who are like, I'm graduating and I want to take the MBLEX, and we're like, okay, we're going to offer a 2-week, course taught by her, like to get you ready to do the MBLEX, that kind of thing. Yeah. It's not a crazy idea at all. Okay. Just don't forget that myosin and actin are the two kind of proteins that help this thing actually contract. And you can actually see a picture here of the power stroke, where the myosin is actually, this two-prong myosin is actually grabbing on the actin and actually pulling it. And that really does happen. I just want to make the physical point that the muscle really contracts. I know I keep saying that. ATP is the energy it uses to do so. Okay. So I already talked about this, but I said those neurons, the wires, they really are wires. I mean, they're not wires made out of metal, but they really are wires in the sense they really can send an electrical impulse, and they're sending information. The neurons, the motor neurons that go to your muscle fibers, they go to what are called motor units, which are just groups of these fibers, and those groups could just be 2 fibers, 20 fibers, 200 fibers, 2,000 fibers. It's very common to see 2,000 muscle fiber units in like your legs, because there's no time in your legs you're not recruiting at least a couple thousand fibers. To do very simple activities in your legs, you need to fire off a whole bunch of fibers. But remember, even if you had motor units going to 2,000 muscle fibers, remember I said there's probably 10 million muscle fibers in your legs, so you've got loads of motor units, and your brain is deciding which ones to fire off or not. But that single neuron can set off the entire motor unit. Not the entire muscle, but the entire group of fibers in that muscle. Yes, Ms. McDowell?
So when the electrical impulse goes to the muscle, like, you know how like sometimes people like bend wrong? That's not the neuron's fault. Is it, you know, like somebody like places their foot wrong and then they like break their ankle? That's not the neuron's fault, is it?
Yes. No, I don't know. I was just trying to think. I don't know exactly how to. I would suspect, for one thing, that people twist their ankle for lots of different reasons. So, I mean, you're saying when somebody steps wrong?
Yeah, like it's not possible that it could like go to the wrong like muscle fiber.
I got you. Yeah. So, by the way, I'm sure there's an exception to everything I tell you in here. But yes, you're right. No, these guys are fairly infallible. That message gets to where your brain thinks it's going. And it's hardwired in that sense. It's hardwired to go to that motor unit, and maybe your brain, I mean, if the accident occurred, it would have occurred all the way up here, but that wire is truly going to the right place and doing the right thing. The misstepping, you're right, came from the ground wasn't even underneath you. You didn't realize that. A mental miscalculation, not paying attention, but it did not come from the wiring, if that's what you're asking.
Those are attached to like the cars, like or where are they actually attached?
They're not actually attached. The wires go right outside the muscle, and there's like a little motor plate, they call it. It doesn't matter. And it releases this neurotransmitter, a chemical messenger, and that seeps in the muscle and tells these sarcomeres to fire.
Okay.
Yeah.
Okay.
And that is, I mean, everything's fallible in your body, but that is not a reported problem. You're right. In general, that's working. Don't get me wrong, by the way, you can have neurological problems where your entire nervous system is not working, but not what you're talking about, the kind of misstep thing. That was a mismessage from up here, probably.
Okay.
Yeah.
Okay.
Yeah. The message, an incorrect message, was probably sent to the correct places. Yeah. All right, I already talked about this, the all or none law, right? You got millions of fibers, but whatever motor unit you set off, only the fibers in that motor unit, it might be one fiber, it might be 2,000, but only the fibers in that motor unit go, and they go full force, and that's it. They don't know anything else. And if you think about the amount of calculations that your brain has to make so that you can lift a pen up and hold it here, it is astounding. Because my brain has to calculate for the weight of this pen. If it goes too much, throwing my arm out of my socket and throwing this pen up to the ceiling. Too little, I don't raise it. It's not just, it's got to fire my front deltoid. It's got to lock down, remember, my rhomboids, my serratus anterior. It's got to make sure my bicep is at a certain point. Probably to stabilize my bicep, it probably kicked in my tricep, not to pull away, but just to kind of keep my elbow locked. Hold all this. There's all these wrist muscles involved. I have to hold the pen without squeezing it really, really hard. All that happens. Thousands and thousands of fibers. And then, by the way, as I hold it here, they're already getting tired. So my brain is turning some of these motor units off and turning other ones back on, and we don't see it. I just hold the pen level. But other fibers are coming on board right now while other ones go away so that I can keep holding this thing. All that goes on automatically. It is one of the most beautiful functions of your body, is that when you do a behavior over and over again, your brain will automate it. If it didn't do this, you literally could not pay attention to me right now, and I couldn't talk to you right now. I would have way too many things to pay attention to. Think about when you learned an activity, maybe snowboarding or biking or something, and it took a lot of concentration, and then you got good at it. And then it started to become something where you're like, oh, I can actually chew gum and actually do something else while I'm doing this thing quite well. Because a lot of the actions have become automated. Your brain's still doing them. It's still working overtime doing them, but it's become automated. I now no longer think about how I walk across a room. I just tell my brain I want to walk across the room, and it takes care of the millions of calculations and nerve firings to do it, and monitoring my balance and everything. Yeah. So I'm making such a big deal out of this because, yes, it's the miracle of the human body, and yes, it's incredible, and that is enough. But think about this as a massage therapist too, because habits in the body become automated. And that can be a very good thing, and it can be a very bad thing. So PTSD is really an automated habit, right? I've gotten a message that when this thing happens, something bad's going to happen, and it's automated back here. My brain's like, no, I figured this out. Don't worry, I got it covered. And I'm like, but I'm freaking out. That's automated. Most of our emotional responses to stuff that really triggers us, and we all have stuff, is automated. It's not necessarily real anymore, but it was real at one time and it became a habit. And so a lot of what we're trying to do with clients is rework habits. They're used to being in bad posture. We're trying to rework that, right? They're used to feeling crappy. And we're really trying to rework that habit. Some people don't realize how good they can feel. They haven't felt good in a long time. And after a while, it just becomes habit. So we really are retraining the brain in massage too. So what you say to your clients is very important for that reason. And remember, you are working with retraining a habit. That's why half of our work is actually very emotional. Not psychological, we can't play psychiatrists, but it is very emotional. I don't care what anybody says. Okay. Oh, and I already talked about this too, so if you need more power, you recruit more motor units. Your brain can't ask them to pull harder because they're already pulling as hard as they can. So your brain goes, well, this group isn't enough. Let's recruit more motor units. And eventually, by the way, it recruits all your motor units, and that's as strong as you are in that area. That's it. That's it. In fact, if any of you started working out at some time and kind of realized that right when you started working out, maybe the first month you experienced pretty big strength gains. Anybody experience this? First month of working out, you really improved quite a bit from where you started, whatever that was. Anybody notice this? Nobody? Anybody? No. Yes. Okay. So we think that most of that improvement that you did the first month wasn't muscle growth, it was muscle recruitment. Your brain got better at talking to your muscles. Because you kept doing the activity over and over again. It's like, oh, here he goes again with the bicep curls. Here she goes again with the bicep curls. I know. It's actually gotten better at talking to that muscle. And it's like, let's recruit everything. Keep going. And it gets better at talking and getting all those muscles engaged and doing that activity. And so you see some real gains. But you're not actually in a way stronger. You're able to recruit more of the strength that was already there. Then later we see, then your gains slow down. And that's when we see muscle growth. That's not that there wasn't any growth the first month, but I'm just saying that really quick gain is quite often just getting better at muscle recruitment. Muscle recruitment. Being able to talk to your muscles and get them to go. Go. All I want you to know is adenosine triphosphate, ATP, is really your cellular energy. It's your gasoline for your body. So you guys essentially, I'm oversimplifying a little bit here, but actually not very much. You essentially eat carbohydrates, break those carbohydrates down into simple sugars. The simple sugars get converted into ATP, and your muscles use the ATP. All your cells use the ATP for energy. When it comes to your muscles, they use it for energy to contract. But all your cells use it. It's the gasoline for your body. And it is a conversion of sugar. Sugar is not a bad thing. Sugar has gotten a bad rap because when you eat a whole bunch of sugar at once, your body's like, I don't need a whole bunch of sugar at once. I need it in tiny amounts all the time. And when you eat complex carbohydrates, it takes your body a long time to break those down into simple sugars, so you get a nice slow drip. You eat a candy bar, you get a whole bunch at once, and it's just too much for your body at that moment. Not that a candy bar is bad, but my point is you don't need that sugar at that moment. That's the problem. Cool. And it was Miss Walker T asked about muscle fatigue. I already answered this, but I'm just piggybacking on it. Runs out of ATP. Literally runs out of the juice to make it go, and it has to fill back up with ATP. It can run out of oxygen too. Your muscles need oxygen to fire, but they can do some firing without oxygen. actually. They just build up more lactic acid and byproducts when they do, and they can't last as long. But you can do some anaerobic exercise. Okay, cool. Okay, questions so far? Miss Estes, you still have your hand up, which is fine. I just want to make sure I'm not ignoring you. That's all. Okay, because that would be unacceptable. Anybody else? Okay. All right. Well, it's going to come as a big shock to you guys, but we have pathologies when it comes to muscles, and I probably assign pathologies to all of you so that you can talk about them tomorrow. So the good news is you only have a 10 question quiz tonight. 10 question quiz tonight that I will release here right now, actually. It lets me. Good. And let me show you your, so you got a 10 question quiz in these pathologies. Let me show you which one you've got. Please pay attention because this is you, right? So, Miss Mares, you have tendonitis. Miss Lobitz, tendinosis. Miss Trotter, de Quervain tenosynovitis. It will take you till tomorrow just to learn to say that. Yeah, tenosynovitis. Yeah, it's almost like I did it to you on purpose. I did not, Miss Trotter, by the way. It truly was really random. Very little thought put into it. But now that I'm thinking about it, I might start doing that. Okay, Miss Hawks, you have fibromyalgia. Ooh, that's a good one for a massage therapist. Really, really is. Myofascial pain syndrome, Miss Estes. We would like a 45-minute presentation, Miss Estes, on myofascial. No, everybody, it's the same game. Please just, I want to walk away and know what myofascial pain syndrome is, and can I rub it? Explain it to me like I'm a 5-year-old, all right? Osgood, oh my gosh, Mr. Brown, Mr. Brown. Osgood-Schlatter disease. Osgood-Schlatter disease. That's a good one. You got that, sir? I hope so. Going once, going twice. Oh,
yes, I got it.
Oh, good, cool. Plantar fasciitis, Mr. Blygen. Another really, really good one for a massage therapist. Shin splints. Miss Allure. Shin splints. Let's see. Mr. Tate, I want to know what strains are when it pertains to muscles. Tenosynovitis. Miss Suriel, tenosynovitis.
Okay, thank you.
Thank you. Gosh, I love it. You're so affirmative. Yes, thank you. Mr. Riedel, epicondylitis. It's just fun to say. Epicondylitis. Yo. Tension headaches, Mr. Placencia. Miss Munoz, torticollis. Torticollis is a good one for massage therapists too, Miss Munoz. You're welcome. I know you're thanking me right now. You're welcome. Miss McDowell, whiplash. Got it? Good. Okay. Miss Jong, I want you to tell us what isotonic contractions are. It's not a pathology, by the way. Just isotonic contraction. I just want to understand what the heck that is, right? Miss Carodi, I want to understand concentric and eccentric contractions, which kind of go along with isotonic contractions. Good luck. Miss Sarno. Hi. Isometric contractions. Do you see that on there? Isometric. That's you. You're going to tell us what it is. Very simple. Keep it simple. We need this simple. Very simple. Miss Walker, why? I want to know what prime movers and agonists are. I think a lot of us already know, but we definitely need to review this. It's super duper important. So don't blow it, Miss Walker. Okay? All right. Miss Walker T, synergists, creating synergy. Miss Vincent, fixators and stabilizers. Seems very appropriate for some reason. Fixators and stabilizers. And Miss Routson, antagonists. And I'm not talking about the annoying people in your life. Antagonists. Yeah? Cool. I think that's everybody. Hope that's everybody. Cool. All right. Thank you, Ms. Routson. I was hoping you'd take it the way I meant it. Sometimes I say